Set two quartz pieces side by side. One is plain, milky white. The other carries rusty amber staining and a tiny brassy inclusion under a 10-power loupe. Color alone cannot tell you which one deserves further testing. 5 physical clues will update the same decision, and one convincing specimen will fail only after it has passed the first 3. Nobody was paying attention to the quartz that George Knight tripped over in October 1850 near Grass Valley, California. That milky white vein rock, pulled from a fault contact in the Sierra Nevada foothills, started the quartz mining era in California and eventually produced $4 million in gold between 1850 and 1857 from the Gold Hill mine alone. The visual difference between that ore and common landscaping quartz? Nearly nothing. That is the problem we are solving today. Every clue in this process updates the same yes or no question, and there is an honest threshold at which the answer becomes leave it behind. A shear zone is a region of rock that has been intensely squeezed and fractured along a fault plane, creating the pathways that hot mineral-rich fluids need to travel through and deposit the metals they carry. Gold does not appear randomly inside quartz veins. It concentrates where those fluids were forced through constricted fractures under enormous pressure, and that almost always means a structural contact, a shear boundary, a fault scarp. Somewhere the rock itself was broken and rebuilt. The iron-stained specimen in our pair came from the fractured wall of a northwest trending fault scarp, visible at the surface as a linear ridge of oxidized rock crossing the hillside. The plain white piece came from a landscaping supply yard with no known geological context, no map reference, no bedrock exposure nearby. One has a geological address, a verified structural setting that tells you why hydrothermal fluids would have moved through it. The other has a zip code, but no street. No reason for gold to have ever paused there on its way somewhere else. Confidence on the iron-stained specimen rises after the first clue. The plain white piece is already out of the running. Iron staining, that rusty orange to deep amber coating spreading across the quartz surface, happens when sulfide minerals oxidize over long exposure to water and air. Sulfides are minerals built from sulfur, bonded to a metal, typically iron or copper, and when they break down, they leave iron oxides and hydroxides behind. Minerals like goethite and limonite that paint the rock in shades of rust. The porous, honeycomb-like cavities those dissolving sulfides leave inside the rock are called boxwork, and the entire rust-capped formation sitting above a dissolved sulfide body is called a gossan. A gossan is a signal that something sulfide-rich once occupied that rock, even if much of it is now gone. Under the 10-power loupe, our iron-stained specimen shows genuine boxwork, a cellular network of thin iron oxide walls, defining spaces where sulfide crystals once sat. This is not a surface rust smear picked up from soil contact. The texture goes into the rock, but orange color alone, without that cellular boxwork texture, proves nothing at all. Iron stains form wherever iron minerals oxidize, and iron minerals appear in thousands of rock types that have never hosted a grain of gold. The boxwork on our specimen keeps confidence rising, but cautiously, because the next 3 clues have not yet had their say. If you want more field guides like this one, subscribe to the channel now. We are just getting to the part that changes the decision. Pyrite is brass yellow with a bright metallic luster, typically forming cubic crystals. Arsenopyrite is silver white to steel gray and prismatic or bladed in form. Chalcopyrite is the brassy yellow copper sulfide, slightly softer than pyrite, and it tarnishes to iridescent blue and green when exposed to air. All 3 appear alongside gold in orogenic gold systems, the kind of deep crustal, structurally controlled deposits that built the Mother Lode Belt in California and the Great Quartz Reef Mines of Bendigo in Victoria, Australia. The Victoria Hill mines at Bendigo pulled more than 1.2 million ounces of gold from quartz reefs between 1854 and 1861. And the ore that carried it was banded and ribboned quartz with sulfide minerals woven through it in layers, concentrated along fault-controlled veins. Our specimen has a small cluster of what appear to be cubic brassy crystals sitting inside a pocket in the quartz matrix. Under the loupe, the crystal faces show striated edges consistent with pyrite, parallel lines running across the cube faces that form during crystallization. This raises confidence further, because pyrite in a banded texture alongside boxwork and gossan in a fault-controlled vein is exactly the association that legitimate gold ore shows. But sulfides are not proof. Barren quartz veins carry pyrite without a single grain of gold nearby. The case is building, but it is not closed. The streak plate and the pick tip are the two tools that resolve the visual argument about a metallic inclusion. The streak plate is an unglazed white ceramic tile that costs under $3 at any geology supply shop. The pick is the corner of a pointed geological hammer, the Estwing E322P, being the standard field choice at $40 to $60. The test is always done on the metallic inclusion itself, never on the surrounding quartz, because quartz is harder than the ceramic and will scratch the plate without leaving a meaningful color. Drag the metallic grain across the streak plate slowly and firmly. Pyrite leaves a greenish-black to dark brown powder smear on the white surface. Chalcopyrite leaves a black streak. A malleable native metal like gold deforms rather than abrading powder from itself, and may leave a faint gold-colored smear rather than a dark one. And when you press the tip of a pick against it, it flattens or bends instead of fracturing. These two behaviors together, malleability under the pick and no dark streak on the ceramic, point toward a native metal inclusion rather than a common sulfide. They are not a confirmed ore grade. They are the screen that tells you whether the next step is worth taking. Pyrite fails this screen every time. It fractures under the pick, angular and clean, and it runs dark on the ceramic without exception. That distinction has cost people real money when they skipped it. During the California gold rush, historical records document widespread confusion between pyrite and gold among prospectors, with large quantities of iron sulfide collected and traded in the belief it was valuable. The entire era that followed, the adoption of streak tests and specific gravity checks as standard field practice, grew directly out of those early, expensive mistakes. Confidence does not close a deal. A $3 ceramic tile does. Press the pick tip into the brassy inclusion on our specimen. The crystal fractures and runs dark on the streak plate. Confidence drops sharply. This is pyrite, not gold. The specimen passed the first 3 clues and failed the 4th. That is the midpoint of the field process, and it is where most promising specimens end. Suppose the metallic inclusion in your specimen does not fracture. Suppose it deforms and leaves no dark streak on the ceramic surface. That changes the decision. Before taking any sample from the field, you must verify that you are on land where collection is permitted, that no mining claims cover the ground, and that your local jurisdiction allows the type of sampling you intend to do. Regulations differ by country, state, and land management authority, and they change. What is allowed as casual use on some public land in one region may require a permit or license in another. Verify your land status and permission before collecting or crushing anything. Do not assume. Where you have confirmed you are legally permitted to sample, a small sacrificial piece of the specimen can be broken away and crushed to coarse sand with a hammer. That sand goes into a gold pan, a shallow plastic bowl with angled riffles from manufacturers like Keene or Garrett at roughly $20 to $50. The panning motion uses water to carry lighter minerals off the rim while denser minerals stay behind. Gold, with a specific gravity between 15 and 19 depending on purity, settles at the base of the pan, while quartz and most silicates with a specific gravity around 2.6, wash away with the lighter fraction. If panning the crushed sample produces no heavy fraction at all, no bright yellow flakes circling at the base of the pan, no dense, heavy minerals settling ahead of the lighter quartz grains, then the decision is already made. No concentration means no reason to continue. Put the rock down. A heavy fraction is not automatically gold. Magnetite, hematite, garnet, and sulfides also concentrate in a pan, while flat mica can flash yellow and drift differently from dense metal. Use a magnet and the earlier malleability screen to sort obvious false positives, but treat everything remaining as an assay candidate, not a discovery. If a heavy fraction does appear, the confirmation gate is a laboratory assay. An assay is a precise chemical analysis conducted by a certified laboratory that determines exactly how many grams of gold are present per ton of crushed rock. Fire assay, the industry standard, uses high temperature fusion to isolate precious metal content and costs roughly $30 to $50 per sample at most commercial labs. It is not a field activity. It cannot be replicated by any backyard process. The assay is the only thing that tells you whether the concentration justifies further attention. Field observations are leads. The assay is the answer. If the quartz has a geological address at a shear or fault contact, keep testing. If it shows genuine boxwork and gosan texture under the loupe rather than a surface rust smear, keep testing. If sulfide minerals are present in banded or ribboned patterns inside the quartz matrix, keep testing. If the metallic inclusion deforms, rather than fracturing and leaves no dark streak on the ceramic plate, verify your permission, then proceed to the concentration check. If panning the legally collected crushed sample shows no heavy fraction at the base of the pan, leave it behind. If a heavy fraction does appear, submit a properly collected sample to a certified laboratory for fire assay before drawing any conclusions. Return now to those two pieces of quartz sitting side by side. The plain white garden center rock was never in the running. It had no geological address, no fault contact, no reason for hot mineral-rich fluids to have ever moved through it. The iron-stained piece, the one with its amber boxwork and its cluster of brassy pyrite, taught the more important lesson. It passed 3 clues out of 5. It had the structural setting, the oxidation texture, and the sulfide companions that make a prospector hesitate before walking away. And then a $3 streak plate and a sharp pick tip ended the argument in 30 seconds. That is the field. That is the same methodical logic that separated productive ore from barren rock in every hard rock quartz mining district from Grass Valley to Bendigo. The rocks do not lie. They just do not volunteer the truth. You have to drag it out of them, one physical test at a time, each one narrowing the decision toward either a laboratory assay or a walk back to the truck.